Assalamualaikum and hello everyone. Today I want to present to you all about performance of decision tree algorithm with randomly distributed feature space. Before I start, I want to introduce myself. Myself is Nurul Raza binti Aziz and I am from RCDCS 2485B and my supervisor name is Sir Muhammad Asbuah bin Muhammad Razali. We continue to chapter 1, research background. Understanding how the distribution of feature in the dataset affect the performance of machine learning models, especially decision tree, is the main goal of the study. Randomly distributed feature space and strategy in which features are dispersed with any predetermined structure or pattern are the subject of this study. Random distribution may increase noise in the data, introduce redundancy or irrelevant feature, and affect decision tree split by making feature selection less intuitive. Logistic regression as a benchmark is a linear model and is often used as a baseline due to its robustness and simplicity. Logistic regression, in contrast to decision tree, assume that input feature and output have linear connection. Problem statement. The performance of decision tree algorithm is adversely affected by randomly distributed feature space due to their dependency on hierarchical split. Logistic regression provide a robust baseline. In such setting, the comparative analysis of these two models under this specific condition was underexplored. Lastly is research gap. Limited comparative analysis exists between decision tree algorithm and logistic regression in handling randomly distributed feature space. We go to research objective. There are 3 research objectives that I got from this research. To analyze how the randomness in feature distribution affect the accuracy, precision, recall, and overall generalization ability of decision tree model. Second, to identify specific characteristics of random distribution that challenge the decision tree splitting mechanism. Lastly is to investigate the condition under which feature space distribution the decision tree perform well. Significance of study. Decision tree sensitivity to examine how random feature distribution impact decision tree performance. Besides feature splitting challenge, randomly distributed feature can make it harder for decision tree to split data effectively. Then, identifying weakness help uncover limitation and area for improvement in decision tree. Then, logistic regression as a baseline. Compare decision tree to logistic regression to assess their strength and weakness. And then, performance comparison. Evaluate how decision tree handle feature randomization versus the linear approach of logistic regression. Scope of study and limitation. Definition of non-parametric tree base. These classifiers, for example, decision tree, are used to categorize data based on input feature. Non-parametric nature. They do not assume a fixed mathematical form or data distribution, allowing them to handle complex and non-linear relationship. Then adaptability. Their complexity grow with training data size, enabling them to fit a wide range of data pattern effectively. We go to limitation. Limitation have 3. First is simplistic relationship. Simulate data, assume linearity which may not reflect real-world complexity. Then, overfitting to noise. Synthetic data, especially with high dimension or excessive noise, can hinder accurate evaluation. Lastly, generalization issue. Results derived from simulated data may not be directly applicable to real-world dataset due to difference in distribution and complexities. Next, we go to chapter 2, literature review. Relate literature on tree-based classification. Decision tree classifier have however not be used as widely by the remote sensing community for land use classification despite their non-parametric nature and their attractive property of simplicity, flexibility and computational efficiency. The non-parametric property means that non-Holman, non-homogeneous and noisy dataset can be handled, as well as non-linear relation between feature and class, missing value and both numeric and categorical input. Literature review about J48 algorithm with simulation dataset. They have 4 literature review about this J48 algorithm. The J48 decision tree or C4.5 algorithm developed by Rosquillen is an expansion of the ID3 algorithm, which allow the target value of new test data to be decided with respect to the different attribute value of training data. As a supervised learning algorithm, a set of example data that consists of relationship between input object and the desired output value is required to develop the J48 decision tree model. Then it improved the ID3 algorithm by dealing with both continuous and discrete attribute, missing value and pruning tree after construction. The J48 algorithm exploited a top-down greedy search throughout the given set to test each attribute at every tree node. The root node is selected based on the attribute with the highest gain value, while the splitting process is determined by characteristics that influence the dataset level of priority. This process continues until the subset become poor, meaning all instead within a subset belong to the same class, at which point the tree grows stop. In the case where the stop rule do not work well, then be pruning process in conduct to decrease the classification error. Performance measure for decision tree. Compared to the statistical and natural approach, decision tree classifier have not been as popular in the remote sensing sector. Decision tree have several benefits, such as flexibility, the capacity to handle nonlinear relationship between feature and classes, the ability to handle data measured on various scales, and the absence of any assumption regarding the frequency distribution of the data in each class. Decision tree can be taught and executed more quickly than neural network. Then they can be applied to classification as well as feature reduction and selection. Classification accuracy is utilized to gauge how well the various approach work. The complexity of the decision boundaries separating the class in feature space, the training sample size, the suitability of the training data in characterizing the properties of the select class, the dimensionality of the data, the characteristics of the classifier used, and the nature of the classification problem all influence the level of classification accuracy that is attained in a given case. Then we go to chapter 3, research methodology, random feature distribution. We use normal distribution. Normal distribution are essential in machine learning, especially for Bayesian inference and Gaussian process. Many machine learning algorithms rely on their properties, even if this is not immediately obvious. Bayesian inference is often interactable, but normal distribution simplify complex integral, making solution more manageable. Understanding normal distribution is key to grasping this concept effectively. Beta distribution. The beta distribution is a continuous probability distribution defined over a finite range of value. It is commonly used to model the probability of binary events such as theta. The distribution is determined by two positive parameters, which is alpha and beta, which influence its shape. The beta distribution is commonly used in Bayesian statistics for modeling probability, and it thus where variables are conceived within 0 and 1. Gamma distribution. The gamma distribution is a continuous probability distribution frequently used to model waiting time or the sum of exponential random variables. It is characterized by a shape parameter and a scale parameter. Next, we go to decision tree splitting with random feature distribution. There are three splitting with random feature distribution. Decision tree are multi-stage decision system that sequentially reject classes until a final one is accepted. They divide the feature space into distinct regions, each corresponding to a specific class. The most common type, ordinary binary classification tree, split the space into axis aligned hyperrectangle using threshold-based decision on individual features. Other type of tree partition the space into convex, polyhedral cell or spherical segment. This approach is especially useful for handling many classes efficiently. Optimum decision tree splitting performance. Importance of optimal splitting directly affect model accuracy and efficiency. Determine the performance of the decision tree. Net splitting criteria, information gains, measure entropy reduction, higher gains means a better split. Gini impurity, excess data set impurity, lower impurity means a better split. Reduction in variance, used for continuous target, increase homogeneity within nodes. Then advanced splitting technique, hyperplane split, use multiple features simultaneously for better modeling. Multiple way, allow more than 2 branches per node, creating shorter, more interpretable trees. Lastly, efficiency and scalability. Finding optimal split can be computationally intensive. Method like fast selection have reduced time complexity and improved scalability. About methodology framework. The figure represents a flowchart outlining a machine learning pipeline, especially involving logistic regression, exploratory data analysis, and decision tree model. Here is a breakdown of each step. Step 1 is the process start. Then step number 2, simulate data by logistic regression model. Data is generated using a logistic regression model. This suggests that the dataset is being treated synthetically rather than using real-world data. Step number 3 is EDA. The generate data undergoes EDA, which includes summarization, visualization, and pattern identification to understand its characteristics. Then, decision tree model. A decision tree classifier is trained on the process data. This model is used to make prediction based on the simulated dataset. Then, model evaluation. The performance of decision tree model is assessed using various evaluation metrics such as accuracy, precision, recall, FI score, and etc. Then, last step is and the process conclude. Simulation with logistic regress. There are 4 steps for this simulation. Step number 1 is defining the linear predictor, which is to specify the coefficient beta for each predictor variable and generate predictor variable from chosen distribution. For example, normal, gamma, beta. Step number 2 is calculating the log or compute the linear combination z equal to x beta. Step number 3 is transforming to probability, which means applying the logistic function to obtain probability. The final step is generating binary outcome. Draw binary response from a Bernoulli distribution with success probability. So that's all from me. Thank you.